di by dt and dv by dt limitations. Transistors require certain turn on, turn off times, neglecting the delay time Td and the storage time Ts. Td and Ts neglected. During the turn on, the collector current rises and the di by dt is IL divided by the rise time, that equals to I collector to source divided by TR. That is equation number 1. During the turn off, the collector emitter voltage must rise in the relation to the fall of the collector current, and dV by dt equal to Vs by fall time Tf to Vcc by Tf. That is equation number 2. The condition of di by dt and dV by dt in the above equations are set by the transistor switching characteristics and must be satisfied during the turn on and turn off. Protection circuits are normally required to keep the operation di by dt, dV by dt within the allowable limits of the transistor. A typical transistor switch with di by dt and dV by dt protection is like this. These are the operating waveforms. The RC network across the transistor is known as a Snubber circuit, and Snubber limits the dV by dt. The inductor Ls, which limits di by dt, and it is sometimes called as series snubber. Let us assume that under steady state condition, the load current IL is freewheeling through the diode Dm, which has negligible reverse recovery time. We have three modes of operation: that turn on, during the turn off, as well as a steady state, that is freewheeling diode is on. So when the transistor Q1 is in on stage, is turned on, the collector current rises and the current of freewheeling diode Dm falls, because Dm will behave as a short circuit. The equivalent circuit during the turn on shown like this. The turn on di by dt is given by input voltage Vs divided by Ls. Now from this, di by dt is IL divided by TR. Now substitute that in this, IL divided by TR equals to Vs by Ls, from which Ls equals to Vs TR divided by IL. Question number 4. Now during the turn off, the capacitor Cs will be charged by the load current IL. The equivalent circuit as like this. Then the capacitor voltage will appear across the transistor, and the dV by dt is given by IL divided by Cs. Now dV by dt from equation number 2 is Vs divided by T fall, which equals to IL by Cs, from which Cs equals to IL T fall divided by Vs. Once the capacitor is charged to Vs, the freewheeling diode will turn on. Due to the energy stored in Ls, there will be a damped resonant circuit as shown in this figure. The RLC circuit is normally made critical damped to avoid oscillation. For unity critical damping, that is L equals to 1, Rs equals to 2 times square root of Ls by Cs. The capacitor Cs has to discharge through the transistor, and this increases the peak current rating of the transistor. So, the discharge through the transistor can be avoided by placing a resistance Rs across the capacitor Cs instead of placing Rs across Ds. The discharge current waveform for the snubber capacitance. In choosing the value of Rs, the discharge time Rs/Cs constant, time constant it is, tau s, should also be considered. The discharge time of 1/3 of the switching period Ts is usually adequate. That means 3 Rs/Cs equals to Ts, that is nothing but 1 by Fs. Rs equals to 1 by 3 Fs/Cs.